Hello, this is the course of data structure and algorithms. And in this video, I would like to explain a little bit about the code that I share to you. So you can get this code in the Google Drive that I already put on the e-class. So you can get the link on the e-class. And there are two codes that I share. The first is the shortest path.ipynb, and the other is the shortest path from the external. I will explain a little bit about this one, so I will leave the remaining explanation to you. Okay, in this code, actually I took it from the book, the reference book that I use, which is from the uh, data structure and algorithms with in Python. Okay, and for the graph, it is related with the chapter 9 and chapter 14. So if you still remember, I already explained to you about the priority queue. So the priority queue has been used in this environment, and you can see the chapter 09 and chapter 14. So just took those in from the Google Drive, and then you can just copy and paste and make sure that you include all the .py. .py means the Python file, so include those .py into your environment. So these are the codes that you can use. So we have the heap priority, we have the adaptable heap priority queue, and we have the partition and graph. The example that I gave to you is using the ads list. So you already know this ads list. We used it before. And the directed means something related with the graph, which is undirected or directed. If it is undirected, then there will be no direction. But if it is directed, then you need to figure out the direction. So one side to another side. So using this at least, you want to define the graph. And let's say I'm using the graph from the figure 1414, which is from the book. Okay. So this graph is about the airport connection, but the airport has the weighted. You already learned the weighted graph. You already learned about the undirected graph, and you already learned about the directed graph. And let's make this as the undirected graph with weighted. And I'll put the figure 1414 as a graph, and then I would like to put this E into the graph E, and then false. So false means this directed equals false. It means not a direction, so it's undirected. Okay, after I have this one, and then I make the graph 2, which is from the figure 1414. Now, in some cases you need to like do the sys.path.append. So in this case, I would like to append the chapter 14, and then I want to use the chapter 14, especially in this case, the chapter 14 shortest path. I would like to use this SPT, and then I want to use the shortest path from the other function, and I want to use it as SPL. Okay, SPT is the shortest path tree, and SPL is the shortest path length. So after we have this, you can define the shortest path length. So this is the shortest path length actually. So if you already do the importing, then you can just reuse it with the SVD. But if you don't have the import function like this one, then you need to define again the function. So this function contains two parameters, the G, which is the graph, and the SRC. The SRC is the node that you want to set as the origin. Okay, this is the code. I think you already learned from the class about the Dijkstra. Okay, and I want to check the shortest path length from the LAX. So once you run this, you can get this is the shortest path. So if you're from the LAX, and then if it is in JFK, then you can see the weight from the JFK to ORD, JFK to Miami, JFK to Boston. Yeah. And then if the key is DFW, then yeah, you can have this and so on. Okay. You can define with the short path length like this one, or you can just use the SPL. So SPL means the shorten. Okay, so the shorten from this shortest path length. So from this definition or from this function. So let's make, if I want to make the SPL from the LAX. So basically they are the same. Okay, so the result is the same, but now it just want to see the LAX. So if you want to see all the items that is related with the RES means this is the shortest path length from the LAX to other nodes. So you can see the key value. And then if I change the origin like to the DFW, then you can see this result. Okay. And yeah, from the book, I also gave you the Floyd-Warshall. Okay, because the Bellman-Ford and the AG is not including in the book, so you can try to figure out by yourself, and if you can find the resources from the internet, that's also fine. So this is the Floyd-Warshall algorithm that has been proposed by the book author, and let's use the figure 1414 as the data for this purpose. So if you run this, yeah, you have the number of vertices 7, then the number of edges 13, and the number of edges in the closure is 21. So you want to know the what is the transitive closure based on the Floyd-Warshall, and you want to know the number of edges, which is the closure edge count. Okay. And the other code that I want to share to you is about the graph. Actually, what you already learned until now is related with the graph with the edge-list structure. Okay. So this is the edge-list structure that you already learned. You were using the edge-list, but there will be another kind of data structure you can use. For example, the adjacency list. Okay. So I would like to inform you that there is one package, we call it NetworkX. I think last time we already used this library. So this library, we can use graph related functions. And also there are some functions related to the shortest path. So you can use Dijkstra, you can use Bellman-Ford, you can use the TAG, and then yeah, you can use various algorithms. They keep updating the resources, so you can just use that one. Of course, I recommend you to try to make your own algorithm, or if you can have the function like in the previous section like this one. Okay, if you can make by your own, then it will be a good experience for you. So in this case, I would like to import the NetworkX. So if I use the add node, then it will add one node. If I want to add nodes from PC, then yeah, I would like to add the nodes in the particular list. So the nodes will be A, B, C, and the edges, there is no edges here, because you don't define the relationship between the nodes. And if you want to use the other way, like the add edges, okay, so I want to add edge, which is 1, 2, and then add HTE, and then another, I will have the asterisk. So the asterisk means something related with the tuple. So if you have a collection of tuple, then it is recommended to use the start or the asterisk. So these functions show us the node of the graph and then the edges of the graph. So this is the result when you add the edge here. Okay. Of course, I will not complain if you are using the code from other resources, but please don't forget that you need to put the reference. Okay, I always respect to you who try to adopt others idea, and you put also the link, so it will be a kind of respectful mind, and it will be a respectful action for other people. So this is from this link, and then this graph actually is based on the adjacency list. So this is another example. Let's say X is the node, and then I would like to know what is the relationship with the other node. So X, it will go to A, B, C, E. And there is also another way to put the node, which is XA7. So I want to know that I know that there is a relationship between the node X and A, and the weighted is 7. Okay. When we want to add the edge, yeah, it's also a little bit different with the adjacent with the edge list structure, because it's using the adjacency. Then when you use the adjacency, you want to add the edges from node to node, and then from to node to from node. So if it is undirected, then you need to define those two. And then the weight, okay, the weight from node to node and to node from node, because it is undirected, then you need to define. When you have this, yeah, of course you can run, and then graph is, yeah, the graph that you want to include. Let's say if I have the edges like XA7, XB2, XC3, yeah, this is another things. Yeah, you can put the edges like this one, and then you try to import it. Yep, this is the edges. So it is the collection of the data actually. And then using the Dijkstra, this is the Dijkstra that I also obtained from the website. Using this Dijkstra, I guess 1 or 2 teams already use this code, so you are already familiar. And use this Dijkstra to figure out the route from the BWI to SFO. Yeah. There is another Dijkstra algorithm. Yeah, I put this link so you can figure out later. Using this link, yeah, we can find the Dijkstra based on the node that I already gave to you. So if it is a graph with, yeah, I think this is the matrix. Okay, if you still remember, we have 3 kind of data structure for the graph: the adjacency list, the edge list, and matrix. In this case, I would like to show to you how to use matrix. So with the matrix, it will show the distance. So it means the node 1 to 1, and this is the node 1 to node 2, and this is the node 1 to node 3, and so on. So we just define the particular distance, and then we can just apply the Dijkstra. And this is the result from the Dijkstra. There is another way also to define the Dijkstra. So yeah, of course you need to figure out what is the best code for your environment. Okay. So in this code, you will see only the distance, but for the next code, you will see all the route from one vertex to another vertex. Okay, so I guess that's all for this code. I will leave it for you, and if you have any questions, please feel free to email me. Thank you very much.